Okay, thank you. Yes, as usual, let me start by thanking the ICTS for giving me this opportunity. My name is Vikas. I'm a postdoctoral research fellow at National Tsinghua University in Taiwan. And let me also acknowledge these funding agencies for funding our love and passion for physics, NSTC and NCTS. So today I'm going to talk about a paradox which we find in game theory in the context of quantum walks and how does it manifest. I hope you can hear me, right? Yeah. Okay. So this is a quick overview of my talk. So first I'll introduce quantum walks and why one should be interested in these systems. And then this paradox, which we find in game theory, and how does it manifest in quantum walk setting. And after that, I'll conclude. So please feel free to stop me. I don't know whether I have time to do that, but still, if you don't understand, please stop me to ask any question. And this talk is majorly based on this article which was published recently in Physical Review A, and it is in collaboration with my current supervisor, Yiping Huang at Tsinghua University. So please feel free to go to this article for more details. Okay, let's start. So let me start with a classical random walk. I know, we all know, but still there is no harm in revisiting it. So in this setting, we have this one-dimensional line, so it's just a space, and we have one walker which has access to this coin. Let's say it's an unbiased coin, and it has two states, head and tail. And every time he tosses this coin, and depending on the outcome of that coin toss, the walker either moves to the right or to the left. So for example, after first coin step, if the result of the coin toss is tail, then the walker shifts to the left-hand side. And he tosses the coin again, and still we get the tail, and so on. And this is like one of the possible trajectory of a classical walker. Another possible trajectory of a classical walker could be something like this. Now, if we ask this question, that what is the probability of finding the walker at ith lattice site after t time step, then what do we find is it looks something like this. So after t 350, and t is the time steps, and this number of coin toss. So after 350 coin toss, we see the probability distribution looks like the Gaussian. Since the coin was unbiased, so there is equal probability of going to the right and to the left, and we find the walker ends up at the origin most of the time, and we get this distribution. Now what we do is we define the quantum counterpart of this classical random walk. Although we do not call it quantum random walk because there is no random, we have unitary processes, so it's just quantum walk. Now what changes? Here we have, we can call it walker or the coin, they are the same thing. So we replace it with a quantum version of that. So since we are talking about a quantum setting, so instead of using head and tail, we would use the spin. So let's say spin up, and the walker is again starts at some lattice site. Then we toss this coin, and in a quantum setting, tossing a coin, basically it will take it into the superposition of up and down both the states. Then depending on the state of that quantum coin, the walker either moves to the left or to the right. But since it is a quantum setting, so the coin can exist in both the states simultaneously or in the superposition. So the walker simultaneously shifts to the right as well as to the left. And this is the first one step of the quantum walk. And we repeat this process again. We again toss the coin, which will bring these individual state to some superposition of up and down. And then again, the walker shifts simultaneously in both directions. And again, we are interested in asking this question that what is the probability of finding the walker at ith lattice site after t time step. And when we do that, we see something like this. So we see a contrasting difference between the classical random walk and quantum walk. One of the classic contrasting difference is the probability of finding the walker at the initial position in quantum walk is minimum at the initial position as compared to the maximum probability at the initial position. And in this case, the walker moves towards both the side towards the boundary. And as we can see, like just in 80 time step, but the walker already reached 50th lattice site. So we can see it's faster. But let's talk about like how faster it is. Like we can quantify it by using the variance, by studying the variance of the position in both the settings. So if we find the variance in the classical setting, it grows linearly with time and commonly referred as the diffusive behavior, as compared to the quantum setting where the variance grows quadratically. And it is usually referred as the ballistic transport. So here we see this like one of the advantage of quantum walks or like over the classical random walks, where we have quadratic faster propagation or spread of the probability distribution. Mathematically, we can write all these steps in such a manner. It's very straightforward. So translation operator looks something like this. It is unitary operator. As I said, like there is nothing, no randomness in the system. And the coin toss is like, because it's a two-dimensional system, so we can take any SU2 operator, which will act as a action of the coin operator. So here we are taking a very simple form. And the unitary evolution or the time evolution operator for one step consists of these two operators. And we can write the state at t time t in this manner, and we can calculate the probability at x and after t times up. Okay, so this is one of the, like this quadratically faster spread in quantum walk makes it a very interesting system to study number of things and to study number of behaviors in many systems. So for example, I'm listing some of them because the literature is vast, but just to name a few, like we can implement quantum algorithms using quantum walk. This has been showed just after the introduction of quantum walk in 2000. We can perform quantum computation, universal quantum computation. Basically, we can create these three universal quantum gates using quantum walk, and we can do this quantum computation. We can perform generalized measurement, quantum task mode, and these things are like very recent, and people have found these quantum walk systems exhibit very exotic phases, topological phases, and these topological phases can be actually extended to the non-Hermitian system, and you can study all these different sorts of property in quantum walk setting, in non-Hermitian quantum walk setting. These three properties are related to the quantum information processing, where we need these states to do certain tasks like quantum key distribution or quantum teleportation. And it has been shown these states, like a maximally entangled state or higher dimensional quantum state or hybrid state, these can be generated in quantum walk setting. So this is one of our work where we showed how can we generate the hybrid entangled state using quantum walk, which are again very instrumental in quantum key distribution like processes. There is another work which is in progress where we are actually working on generation of entanglement. Like we can generate maximal entanglement in the system, and not just the maximum, but we can actually have some correlations which are robust against certain noise. So this is right now in progress. But for today's talk, I'm going to talk about this work. So let's see what is the setting. So imagine there is a shop, and in the shop there are two counters, and at both the counters there is some game, and you can see whether you are interested in those games or not. But what is the first game on the first counter? So game A is, so you enter and you have certain, let's say you start with 100 rupees and you toss one coin, and there is a winning probability of the coin, let's say P1, and there is a losing probability 1 minus P1. So if you win the toss, then you win 1 rupee. So your capital will grow, and if you lose, your capital will decrease. So this is game A. Right now we don't know what is the P1, so we will see. There is another counter. At another counter, we have another game, which is which progress depending on the capital that you have in your pocket. So if the capital or the rupee, let's say if you have 100 rupee, and they ask like if it is divisible by m, then we toss a coin 2, which has again certain probability of winning and certain probability of losing. And if it is not divisible by m, then we toss another coin 3, which has again some parameters. Now if we fix these parameters as these, so P1 is like half minus epsilon, epsilon is this number, and P2, P3 is this. And for the time being, just for the illustration, we can take m to be equal to 3. And we can see, like, since the probability of winning is less than half, so if you play this game A for, let's say, 100 times, you will lose all your capital, right? Because we can clearly see it's a losing strategy because the probability of losing is less than half. For game B, at present, like it looks like, because P3 is 75%, so it looks like that you might win, and that is what you think. So you go to counter B and you again play this game. So you initially, there is some zigzag, you win, you lose, you win, you lose, but over the time, you lose all the capital. So individually, when you play these games, you end up losing all the capital. You get frustrated, you come again next day, and then you decide not to play these two games. But you just randomly decide, okay, first I go to the first counter, then I go to the second counter, some random thing. Or better, you have a coin, you toss the coin, and depending on the state of the coin, you decide whether you want to play game A or B. When you do that, what you see, by randomly choosing these two games, which were individually losing games, you can actually increase your capital. So this is very counterintuitive, and that is why the paradox. And in this scenario where you randomly select to play game A or game B, you end up increasing your capital. You can do better. Instead of introducing this randomness, you can actually decide some periodicity that, okay, first you will play game A, then game B, then game A, then game B. It's even more better. Like if you decide to play these two games in some periodic manner, again, you end up winning the game. And that is the essence of this paradox. The combination of two losing strategies can become, or can give you a winning strategy, or vice versa. The two winning strategy can give you one losing strategy. So this is the paradox, and this is what we are. And the example that I gave you has nothing to do with quantum. It is the original setting which was introduced in 2000, and now we are interested in how this paradox manifests in quantum walk setting. So in quantum walk, what we do is we can define these games. And how do we define these games? So for example, after and by game here I mean the choice of the coin, because the translation operator doesn't have any control over it, because it has to move to the right or to the left. But the coin, we can select the coin, and coin will decide whether it's game A or B. And for a given state, if the probability of finding the walker is less on the left hand side, so I assume this is the origin and this is where we start. So after time t, if the probability of finding the walker on the left hand side is less than on the right hand side, so basically the expectation value is greater than 0. So it's like a winning strategy or winning game. And the vice versa, we can define what is the losing criteria. So now in a quantum walk setting, we have two games, and we have decided, like, we have a game and winning criteria and losing criteria. So what we do is, so here we define, first we need to define two games which are losing strategies. So for example, here we have one game A, CA, and another game CB. Now the only trick is here the CA is space and time dependent, but the coin B, we make it space position dependent in such a manner. So this form is motivated by the recent experiments, and we can realize such kind of modification in experiment. So we fix these parameters and we fix the initial state. Now when we evolve this quantum walk using these two operators, so this is what we see. So if we choose the coin A, the expectation value decreases with time, and for another game also it decreases over time, and we don't see bounce back. So it is individually these two games are losing strategy. Now when we combine these two coins in such a manner, for these choices of M and N, we again see this is again going negative all the time, and we can see the probability distribution. The probability current is on the left hand side. But for a special, right now we don't know whether it is something special or not, but once we choose M and N to be 2, 2 or 2, 1, we see the probability current shifts to the right hand side. And here also we see this is the probability current, probability density, and we see the two individual coins which were actually giving a probability current in the left hand side can combine to give a current on the opposite side. So this is like two losing strategy are becoming the winning strategy. So this is like Paranda paradox, and we actually take all these parameters theta b and theta minus, so which we had here, because there is nothing special. We see there is nothing special about these parameters. We can in principle select this. So in these figures, the blue region represents the losing strategy and the red region represents the winning strategy. And actually we can see here the blue region is becoming the red one. And here also we can see blue region turning into the red one. So there are like many spaces where we can actually realize this Paranda paradox. Okay, so we can do the same thing, but in this case, rather than making the coin space dependent, we make it time dependent in such a manner. Again, it's SU2 with some different parameterization. And here we choose two coin to be like this. And it's a very linear dependence on time, which is again very easily implementable in experiment. And we choose the initial state. And again, when we evolve the quantum walk with these two individual coins, we see the probability current is always towards negative x direction. And if we combine them in such a manner that we use CA square at even times and CB square at odd times, we can actually reverse the current in the opposite direction. So, so this is in the quantum walk with time-dependent coin. So that is why it's the inhomogeneous quantum walk. And I think I have, yeah. So just like one slide more, I'll talk about what was the motivation of this work. So the motivation was like, this is like a slightly different idea of quantum walk, but it's the same. It is just that we write our one-step time evolution operator in such a manner where we have theta 1 and theta 2. So this system is translation invariant, and we can actually go to the Fourier space, and we can write this block diagonal Hamiltonian. And we can actually study because this Hamiltonian has certain symmetry, so we can actually study the topology of this Hamiltonian. When we do that as a function of this theta 1 and theta 2, we find this quantum walk, this split step quantum walk, exhibit these non-trivial topology. And you can see here, so this is like combining the two strategies. So that was our motivation to actually see if we can devise some advantage of a winning strategy when we have non-trivial topology. So this was the motivation. But in this present work, we were not able to establish this one-to-one correspondence. But the work that we are doing right now, in that case, in that setting, we are seeing some structure like this, but still we don't know. Yeah, with this, I summarize my work, and yeah, this is the quantum version of Paranda paradox we showed in the quantum walk setting, and we did not use higher dimensional coin and decoherence system because the past result about the Paranda paradox in quantum walk, they introduce higher dimensional coin or they introduce the decoherence in the system to actually show the Paranda paradox. And this is some of the outlook, as I mentioned, to find out if we have a topological advantage in designing the winning criteria or more generalized strategies, and if we can define or we can come up with different criteria for games to win and realize Paranda paradox. Yeah. Okay. Thank you.
Thank you, Vikash. Questions? Yeah. So, Lalo, yeah. Take it away, Lalo.
Hi, thank you for the nice talk. I was wondering, so you showed that in the quantum case, the average can increase or decrease as well. I was wondering how is the distribution, no? Because in the first case, you showed that you have like a bimodal kind of distribution. So I was wondering.
So for example, if you see here, yeah. So this is the distribution. So here is the density plot. So on x-axis, we have the lattice, and on y-axis, we have the time.
Okay.
So yeah, it's not really clear, but you can see one line, right?
So okay, but you have like bimodal as well.
Yeah, exactly. It is just that the probability on the left-hand side is more than the right-hand side, so that the expectation value is less than 0.
Mm-hmm.
Yeah.
Thank you.
Yeah, thank you.
Yeah, so any other questions? So I had a question. So you had the winning and losing strategy in a kind of very nice plot for this one.
Yes.
So, I mean, it's just a curiosity for me, right? But it looks a little bit, it has a self-similar structure to it. It looks a little bit interesting, reminds you of Mandelbrot or whatever. Is there some interesting mathematical feature here, or is it just coincidental?
I mean, we are also asking this question to ourselves. And so far, as I mentioned, for example, in this slide, so we have these two parameters, theta 1 and theta 2. So we were actually expecting such kind of structure to come out.
I see.
So in the blocks, like in the blocks where we have 0, so we should have the blue region where like it's losing strategy, and in this region we were expecting, but we could not get. And because we are choosing the coins to be like space or time dependent, so we are breaking the translation invariant. So we cannot do the Fourier analysis in this case. So that's even more difficult.
Can I just ask just one more quick question? Is there an explanation of these, so they look like beetle leaves,
right?
Like,
this one?
This one. Is there, what is the explanation of that heart shape?
Honestly, I don't know.
Okay, fair enough.
Yeah.
Okay.
As I said, like the motivation was to maybe in the, so as I said, like we got something. So in the next,
Fair enough. Yeah, it's very pretty.
yeah, it looks pretty. Yeah.
Any more questions? Okay, then let's thank Vikash once more.
Thank you.